We continue reviewing linear algebra. Consider two bases B1, B2, and C1, C2 for vector space V such that B1 and B2 given like that. Suppose X is B1 plus 2B2. So that is, we start with X in the coordinate B is 1 and 2. Meaning that it is 1B1 plus 2B2. And now we're going to use B1, C1 minus 6C2 for B1 and 4C1 plus 3C2 for B2. And we substitute into that. B1, I'm going to use this. C1 minus 6C2. And then plus 2 B2 is this. Right. So we just have C1 minus 6C2 plus AC1 plus 6C2. It just happened that 6C2 and 6C2 here cancel out. So we have 9C1. And there's no C2, so we can just say 0 C2. So in that case, we can say if we want to write X in the coordinate of C, we're going to use 9 and 0, meaning 9C1 plus 0 C2. Right. Next, let B be this and C be that. Be basis for R2. We are given this. Change the coordinate of, find the change of coordinate matrix from B to C. So the change of coordinate matrix from B to C given by B, we go from B to C like that. And the way we do that is we do the reduced row echelon form of the following. So first we're going to stack the vector C1. There's only two vectors here. And then we stack B1 and then B2. And then we do the reduced row echelon form. It will give us the identity matrix on the left, and on the right we have that matrix. Notice C and B in that order, but the arrow going backward from B to C. Right, so that's what we have. So we're just gonna do that pretty much. C1, C2, 1, 3, -4, -10, and B1, B2. Right, just do the reduced row echelon form here. So that's what we have. So we should have the identity matrix on the left hand side, and on the right hand side is the matrix that we want. So that's what it is. So the change of coordinate from B to C is given by this matrix. Right, pretty much just that. Right. Next, for the given matrix, for the given matrix, we have the matrix and the eigenvalues of 5. Find the eigenvector corresponding to the eigenvalues. So this pretty simple. We will find the eigenvector. So when we find the eigenvector, we will solve the equation A minus lambda I times V equal to 0 vector. Here we know lambda is 5. So what we do is we're just going to start with, let's write the equation. So we take the matrix A, subtract the lambda, which is 5, on the diagonal entries. Times vector V equal to 0 vector. Right, so just write like that. Let's fix this real quick. That better. Right, so that gives us 32 minus 5, that's 27, minus 9, 108, minus 36. Right. That is the romantic matrix, and we'll just do the reduced echelon form. By the way, this is only the 2 by 2 matrix, so we should have one row is the multiple of the other. Usually for this we just should be able to do this by hand. Because the second row must be 0. Sorry. Because the homogeneous system of equation, we should have infinitely many solutions. That means we have to have the whole row of 0 at the bottom. We don't even need to use 0 on the last, because it doesn't matter what we do, it's going to be 0 anyway. So it's 108 and negative 36. Right, convert to fraction. Right, that 1 negative 1 over 3 0 0. Right, now because the pivot is here, we can say x1 minus 1/3 x2 equal to 0, where x2 is 3. So with that we have x1 is equal to 1 over 3 x2. Right. With that we write the solution as x, we should use v here, but let's say use v. x1, x2, x1 is 1 over 3 x2, x2 is 3. So if we pull out the x2, we have 1 over 3 and 1. Now, of course, we can just use that vector, but usually for eigenvector, we choose x2 to be something nice, so we don't have to deal with fraction. In this case, I choose x2 to be 3. I will take 3 times 1/3. 3 times 1 over 3 is 1. 3 times 1 is 3. So that's what we have. So that is the eigenvector corresponding to the eigenvalues of 5. Right. Now we do the same thing for this one with eigenvalues of -3. Once again, we find the basis for eigenspace for the given eigenvalues. Right. So what we do is we're going to solve a minus lambda I times v equal to 0. Right. So we take the matrix A and subtract the diagonal entry by -3. Right, times v equal to a 0 vector. Right, now simplify this. We have 1, 3 to be 4, -4, -4, -4, -4. So that's positive, sorry. And 4. Then 4, -4, -4. Right. Of course, when all of this cancel, we just have 1, -1, and -1 on the first row. Anyway, just want to do this very systematically. Just do reduce to echelon form. Like I said, if we do this by hand, 1, -1, -1, easily, because this row cancel that row, this row the same, so subtract that row will cancel also. Right, so we just use reduce to echelon form here. Again, the last column of 0, we really don't need that to put in the matrix. It's going to be 0 anyway. Oops. So for that, we can have the first x1, x2, x3. Let's use v in this case because we're solving for v. And the pivots on v1. So we say v1 minus v2 minus v3 equal to 0. V2 and v3 are free. Right. So that gives us, we can write the solution as follows. V, we have 3 components, v1, v2, v3. V1, if we solve for it, will be v2 plus v3. and then v2, v3. So if we split for v2, there's 1 and 1 and 0. For v3 will be 1, 0 and 1. So with that, we can just use that and that as the vectors, the basis for the eigenspace. So we just have the space that's spanned by these two vectors. Right. Next, on this class 2 problem, we are given eigenvalues. Now, if we don't know the eigenvalues, we just have the way to find it. And to find the eigenvalues, we equivalently to find the characteristic equation. So characteristic equation is pretty much just determinant of a minus lambda I equal to 0. It is an equation. So it's that. Now all we do is just find the determinant, which use the two vertical bar, the diagonal entry of minus lambda on the diagonal. Right. Good thing from here, what we have here is this is the upper triangular matrix. So the determinant is just equal to the diagonal, the product of the diagonal entries. So from here we just have 2 minus lambda times 4 minus lambda times 8 minus lambda, and then 2 minus lambda again. So two of them we can combine. And we show that equation, and that will be characteristic equation. Pretty much just that. Right. Next, we find the eigenvalues and eigenvectors for the following matrix. For this, first we find the eigenvalues. After that, we find the eigenvectors. So step number 1. Find the eigenvalues. Meaning we solve this characteristic equation, that is a zero number, not a zero vector. Right, so we have determinant 2 minus lambda on the diagonal entry and then we just find determinant. So cross multiply, and then subtract the order diagonal. So that gives us 10 minus 2 lambda minus 5 lambda plus lambda square plus 1 equal to 0. So we have lambda square minus 7 lambda and plus 11 equal to 0. Right, I have to pause the video because this equation doesn't have a nice answer. So let's change something real quick and make that a 2. That will be much better. We have the system of lambda minus 3, lambda minus 4. That gives us this equation. Right, so from here we have lambda equal to 3 or lambda equal to 4. Right, I will denote lambda 1 to be 3 and lambda 2 will be 4. Right, so we found the eigenvalues. Next we find the eigenvectors. Meaning we will solve the equation a minus lambda I times v equal to 0 vector. Right, first for the lambda of 3, do that. So the matrix minus 3 so that is a minus lambda I. Now times vector v equal to a 0 vector. Right, so that gives us negative 1 and 2, negative 1 and 2. Yeah. If there are 2 rows, there should be 1 row is the multiple of the other. But still, reduce to echelon form. If you do that, we should have 1 and then negative 2 and 0. Again, I really don't need to write the last column of 0. I said we don't really need a calculator for this, but when we have 3 by 3, it will help if we have a kind of systematic way to do things. So from here we can say v1 minus 2v2 equal to 0 and v2 is 3. Right, so we can write v as the vector of v1, v2. From here we can say v1 is 2v2 and v2 is 3. Factor out v2, we have 2 and 1. And usually after this stage we just choose v2 to be something, so we have the vector that is nice and even. So we just choose 1, so we have the vector of 2 and 1. And that is the vector v, the eigenvalues corresponding to this, so just call that v1. Next, we will solve for lambda 2 equal to 4. So we take a diagonal entry, diagonal entry minus lambda. That gives us negative 2, 2, negative 1, and 1. Right, to deal with echelon form, we should have 1, negative 1, and 0. Yeah, just try to get 1 here, and then the second row must be the same. Or second row, when we do the real echelon form, that should be 0, because we expect to have a free variable. So for that, we have v equal to v2, and v2 is free, so just have v2 1 and 1. Yeah, v1 is v2. So in that case, we just choose v2 to be something so the vectors come out nice and even, and we choose 1. So we have v2 is just 1 and 1, and that is v2. Right. Next problem. Find eigenvalues and eigenvectors for the following matrices. Right. So first, find eigenvalues. Meaning we solve the equation determinant of a minus lambda I equal to 0. Right, so determinant. This should be easy because that is the upper triangular matrix. So upper triangular matrix, so we just multiply the diagonal entries. So that gives us lambda equal to 1. Right, next. Find the eigenvectors. Meaning we will solve the homogeneous system A minus lambda I times v equal to 0 vector. Right, so take the matrix A, subtract the lambda, which is 1, just subtract lambda on the diagonal entry times v equal to 0 vector. Right, so that gives us 0, -2, 0, 0, 0, 0. Right. Right, let's put this in the augmented reduced to echelon form. Right, so we just have that. So let's say we have v1, v2, v3, and so v1 is basic. I mean v2 is basic. We can say v2 is equal to 0, v1 and v3 are free. Right, so we write the solution as v is v1, v2, v3. V1 is free, so just v1 it itself. V2 is 0, v3 is free it itself. From this we can write this as v1, there's 1 v1, there's 1 v3, like that. So we have two vectors, 1, 0, 0 and 0, 0, 1. So those are the eigenvectors, and this is eigenvalues. So it's not that bad, since we can use the determinant of upper triangular matrix. It could be bad if we don't have that. Right, next. Find the formula for A sub k given that A can be decomposed as P d P inverse, where P and D are given as follow. Right, so simple enough. So let's say it, we have A equal to P d P inverse. Now what we want is A to the A power. We do that A times, and the middle two combined is just the identity matrix. Anything times the identity matrix is itself. So when we do this, we just have P d to the 8 P inverse. So we have the matrix P times the matrix D to the A power, and then the matrix P inverse. Right, so P is just that. I don't know, just to the k times, not the a times. So that gives us 7 to the k, 0 and 0, 8 to the k. So for the diagonal matrix, the matrix only have diagonal entry when raised to the k power. We just raise each diagonal entry to that power. And then the 3, 1, 2, 1, I just find the inverse of that. Of course, invert 2 by 2, there's a formula for it. Right, give us that. Right, now just multiply this out. 3 row times column, so 3 times 7 to the k plus 1 times 0, so that's 0 and 8 to the k, and then row times column, row times column. So now we just row times column, row times column, so we have 3 times 7 to the k minus 2 times 8 to the k, right? And then row times column, row times column. Now times this column. Right? And the second row times that. Sorry, that should be negative 3 times 8 to the k. Right, so that is an advantage of diagonal matrix when raised to a power. Just multiply, just raise that diagonal entry to that power. And so if we can diagonalize the matrix to this form, and that will be very simple. Right. Next, diagonalize the matrix A if possible. That is, find the invertible matrix P and D. So this time we are only given the matrix. Now we just have to find the determinant and all of that. So that requires a little bit of work. Let's take the first step is solve the characteristic equation, and after that we find eigenvalues. Meaning we will solve determinant of A minus lambda I equal to 0. right? Determinant 1 minus lambda on the diagonal entry. Right. So this case, if it is easier to find the determinant based on the second row, so the sign will be plus minus plus, so that will be plus. So I will write this as negative 4 minus lambda, and I'll just go over the row and column. What's left is 1 minus lambda, 4, negative 5, negative 8 minus lambda equal to 0. Right? So let's multiply it out. Negative 4 minus lambda, and subtract this. We have 1 minus lambda minus 8 minus lambda plus 20 equal to 0. So minus 4 minus lambda, and this will have 8 minus 8 and 20, so that's 12. And minus lambda plus a lambda, so that's 7. And then plus lambda square. Right. Luckily we don't have to multiply this out any further. So here we just factor minus out. We just have minus 4 minus lambda minus 3 lambda minus 4. Wait a minute. That plus 8 minus lambda, so that's a plus. Therefore, these are plus. But wait, if I take the minus outside of this, then both of them to plus, you have 2 of this. So I have lambda plus 3 and lambda plus 4 square equal to 0. So when we do this, what we have is lambda equal to 3, negative 3, multiplicity of 1. And lambda plus 4 equal lambda equal to negative 4. So lambda equal to negative 4, multiplicity of 2. Usually if it is that long, it is much better to write like this. Lambda 1 is equal to negative 3, so there's only one of them. And lambda 2 and 3, that's multiplicity of 2, is negative 4. Right, so one of this and 2 of that. So the first step is find eigenvalues. And now to find eigenvectors. Is where we solve the homogeneous a minus lambda I times v equal to 0 vector. Right. First for the eigenvalues, -3. Right. So I have the matrix A. Just need to subtract the lambda to the diagonal entry. It was 414 0 0 -1 0 -5 -1 and -5. Right. Reduce to echelon form. Right. Like I said, I don't need to enter the last column here. All of them is going to be 0 anyway. Right. We have that 1 0 1 0 1 0 0 0 0. So from here we have the pivot on v1 and v2. v3 will be free, and this equation v1 plus v3 is equal to 0. v2 free, sorry, v2 is equal to 0, right? And v2 is free. So with that we have v equal to v1 v2 v3 v1 will be negative v3, v2 is 0, and v3 is free. So that gives us v3 -1 0 and 1. And we choose v3 to be something nice. I mean something so that the vector is nice and even. I just choose 1. So I have v3 as the vector will be -1 0 and 1. And that is the vector corresponding to this eigenvalues of -3. So that's what we have. Next, we have lambda 2 and 3 equal to -4. So we have the vector 1, 1 and 4. So we subtract -4 on the diagonal entry. Give us 5 1 4 0 0 0 negative 5 negative 1 and negative 4. Reduce row echelon form. Right. So let's change this to fraction. So we have only one pivot here for V1, and V1 plus 1/5 V2 plus 4/5 V3 equal to 0. V2 is 3, V3 is 3. So with that, we write the equation as right. If we solve for V1, we have to subtract this on the other side, so negative 1/5 V2 minus 4/5 V3. V2 is 3, V3 is 3. Right. So we have for V2 negative 1 over 5, 1 and 0. For V3 negative 4/5, 0 and 1. Right. Now, of course, we can choose this vector, but we choose some multiple of it so that we don't have to deal with fraction. So with that, I think it's better multiply this by 5, so we have negative 5. Multiply by 5, right? 5 and 5 cancel out, so it's negative 1. So multiply by 5, negative 1, multiply by 5, and the other vectors multiply by 5, negative 4, 0, and 5. So put that together. Sorry, can't run out of space here. We have the matrix D will be the diagonal matrix of the eigenvalues negative 3, negative 4, and negative 4. And P is the eigenvectors corresponding to this. So V1 is negative 1, 0, and 1. The other one is negative 1, 5, 0, negative 4, 0, and 5. Right. Right. Timestamp. Right. Next two problem I will do together. That's simple enough. Just the inner product. V dot W. So if we write like that, we can say two components of 15 and 5 dot 12 and negative 6. So the first with the first plus the second with the second. Negative 210. Next you have v dot w. Now vector 4 component. Two times 3 times negative 2, so times 1, negative 1 times 5. So that cancel out. That's 6 minus 6, 0, so that's just negative 5 here. Right, very straightforward. That's the inner product or the dot product. Timestamp. Find the unit vector in the direction of the given vector. So let's say this vector is the vector v. We find the unit vector in that direction. So first we find the magnitude of v and then we just divide that from v. So unit vector in direction of v is given by v divided by the magnitude of v. V is just going to say 3 component. The magnitude is just given by Pythagorean theorem. (32 square plus 32 square plus 16 square 23, and take square root of that is 48. Right. That's simple enough. We just split and we have negative 32 over 48, 32 over 48, negative 16 over 48. So divide by 16, negative 2 over 3, 2 over 3, and negative 1 over 3. Right, so we can write the vector in this form, or we can, if we want to be consistent with this, we can just put them as a column vector. Right. Next we find the distance between two vectors. So the distance between two vectors is given by just the norm or the magnitudes or the length of the difference. So we just subtract them. So that gives us 25 minus negative 3, so that's 28. 16 minus 2 is 14. 21 minus 7 is also 14. And so pretty much we just have square root of 28 square plus 14 square plus 14 square. 1176. We have square root of that. Right. We can just leave it like that. Find the angle between two vectors. Round to one decimal place if necessary. Right, so the angle between two vectors. So first we have these properties of the dot product or the inner product is equal to product of the magnitude times the cosine of the angle between them. So if we want to find the cosine of theta, we take the product, the dot product over the product of the magnitude right, divided by the magnitude. That gives us 2 times 1 plus 1 times 2 plus 2 times 3. So that's 10. And this is square root of 9, which is 3. And then square root of 14. So we have 10 over square root of 9 times square 14. 9 times 14 is 126. Right. So cosine is equal to that. So we take theta equal to cosine inverse. Where's the 1? Alright, so that is in radian. But if we do the inverse, it's better to give the answer in degree. Try that again. About 27 degrees. Right. When we're done, just go back to radian because that is the default. Should be the default option for the calculator. Right, so we have that. Find the orthogonal projection of y onto u. So projection of y onto u is equal to y dot u over u dot u times vector u. Vector y is 8 and negative 24, and vector u is 8 and negative 4. The dot product itself so 8 times 8 64 plus 96, that's 160. And down 8 times 8, 64, 4 times 4, 16. And down times 8 and negative 4. Right. So that is 160 divided by 80, 8 and negative 4. So that gives us 2. 160 divided by 80 is 2. 8 and negative 4. So that's 16 and negative 8. Right. I pause the video here. We'll continue on another video for linear algebra review.